Hey folks, welcome to another episode of ASP.NET Core from Zero to Overkill. In this episode, we'll play around a bit with BenchmarkDotNet and analyze the performance of some of our code to see if we can improve it, and while we try to improve it, see if our changes are really doing something useful. So in the previous episode, we introduced ProxyKit to our backend for frontend in order to simplify the request routing. But while we did that, among other things, we created a new class to help with matching the incoming requests to the correct backing API. While this class will run in all requests, so it's important for it to be as performant as possible. So it gave me the idea that we could play around a bit with benchmark.net to see if we have the best solution, how we can improve it. And of course, I will probably not get to the best solution, but feel free to open issues or create a pull request to improve what we get out of it. But like I'm saying, in this episode, we'll use benchmark.net to check out this class, to map a base route to the target API route. We'll start with the simplest solutions that come to mind. So the code that was committed as part of episode 29 is already not the simplest solutions, because I thought of the simple solutions, implemented it, and then remembered other things. But in this episode, we'll basically redo those steps. So we'll start with the simplest solutions, then try to improve and see what we get out of there. So while we start with the simple solutions, then we'll use benchmark.net and analyze the results, not only in terms of execution time, but also memory allocation, which is also an important metric that many times maybe we don't take into consideration. And I'm talking about myself in the past, when before existing benchmark.net and other tools, and or better yet, I didn't know better that we should use tools like this, because probably there were other tools, maybe not as good, but probably there were other alternatives. But in those times, I simply use the stopwatch, then do a for with some iterations, then grabbed the average result in terms of timing, and okay, this is how I compare performance. But there are more things to it, and a library like benchmark.net really helps us to get a better picture. So we'll start with the simplest solutions, analyze the results, and then we'll do some more iterations on those ideas, and we'll explore some concepts like using the span of T, which is a newish type that appeared on .NET Core 2.1, if I'm not mistaken. And also method inlining, which is just to play around with it, not very important in this case, but for sure in other scenarios it is very important. So the usual plugs: if the videos are being useful, please like, share, and leave feedback, being that this third one is the more important, but the other ones are also nice and help the channel grow. And also remember that there is always, or almost always, but at least for this series, always an accompanying blog post on the blog. For more info, you can also go to Twitter, or if you need other contacts, feel free to visit my site. With this out of the way, let's get to it. So let me get back here to the list, and let's start maybe by taking just a quick look at what is benchmark.net. So benchmark.net is an open source library that helps us with benchmarking, of course. You can see here the project GitHub. So like I mentioned, the problem is that writing benchmark code by hand is not easy, and BenchmarkDotNet helps us with that. So we don't need to write those fors and stopwatches and stuff like that were not the best way to do it. So BenchmarkDotNet does a lot for us. We just need to write the code we want to benchmark, then we can prepare how to call it, using attributes, using regular imperative code, and it will do most of that for us. We'll see. It's better seeing than trying to explain. But besides that, it also has a lot of other features. For instance, besides that, we do just running the code in the iterations. Not only does it do that, but for instance, does warm up, which might be important. We can test on multiple target frameworks, not just .NET Core. In our case, we just need .NET Core because it's where our code will run, but maybe we were writing some library that should be used across frameworks. We could do that. We could use different architectures, different JIT versions, GC, flags, and so on. So BenchmarkDotNet does a lot of that for us and simplifies a lot, but we'll see how to do it in just a minute. So, getting back here, we'll start with the simplest solutions. So, let me back to the code. Just for you to get localized, what I did was in the server part. So in the web frontend repo, we have the server, and in here, in the solution folder, I created a new folder called benchmarks because we don't need to mix the benchmarks with the usual code. So created a new folder, benchmarks, and in here creating the solution for the benchmarks and a project for API routing, which will only have the code for these benchmarks that we will do today. Maybe in the future we need some more benchmarks, we can create other projects. So I'll go here, and that's it. One thing to keep in consideration, because I had problems with that in the past, is the size of the path, because not only is this path a little long, but when running, BenchmarkDotNet will create some more files in there to run, and the executables and stuff like that to run in isolation, and it can be even worse in this regard of the path size. So if you have some strange errors that you don't understand, try that. I already tried in this path and it worked, so hopefully no problems, but be aware of that. Let me clean this up. So let's go to the code. If you remember from the past episode, or if you don't, but we'll work on that. What we need is basically a class that, given a route, which is the path of the request that we received, can analyze that route, grabbing the beginning and match it to a backing API that it needs to be matched, or not if we can't find. So because we are going to create a bunch of classes to benchmark, I think it's a good idea to create an interface. So let's start with that. Let's add an interface. As usual from the past episodes, I have already some code prepared on the side, so the videos are not that long. So created an interface, and we just need one operation. So this operation is the one we need from what you did in the past episode. We want to receive a path string, And if it matches to something, we want to output an endpoint, and we do a bool just to so we can have the logic to know if it's there or not. This is annoying us because path string is from ASP.NET and this is a console application, so we need to go to NuGet and HTTP abstractions, exactly this one. We'll add this package. Okay, so this is the first. This is the interface, very simple. We'll use it when benchmarking. Now, for me, thinking about this problem, the first thing that comes to mind is, so we want to map something to something, so we'll use a dictionary. So that was exactly the first thing that I thought and implemented. So let's create a class here with that implementation. Add a new class. And I'll just copy the implementation in here to be faster, and we'll quickly go through it. So what do you not like? Importing things. Whoops, I removed the class. Okay, this is what I want. Okay, so let's try to see this quickly. We start with the constructor where we get a dictionary of string that maps a base route of our BFF to the base route of the backing API microservice, whatever, to where we want to route. We get that. So in here, let me try. So we need to play around with this path to grab the beginning. So we just want the first segment. So I'm doing this, all of these shenanigans with strings and substrings and stuff to find out that that first segment. And when I finally get the base path, I'm trying to get from the dictionary to get the endpoint and return true or false depending on if it exists on the dictionary. So this seems good. I think, at least for me, it was the first thing that came to mind. But then another thing came to mind, which is all of these string manipulation. So I would bet, even without benchmarking, that this solution is fast, which is important. But at the same time, because we have to do these string manipulations, if you recall correctly, in C#, in .NET, strings are immutable. So anytime we manipulate a string, we are creating a new string. So just to do this analysis, we are creating new strings. Now, is this a problem or not? Maybe yes, maybe not. Ideally, we would like to not allocate more memory. So if we could do this without it, it would be the best. But we can't. So I started thinking, what are other alternatives? So another alternative really simple is, instead of a dictionary, we could just have an array with a route and iterate over the array and find it. Supposedly, if we don't have a lot of endpoints, this should be fast. So how could be an implementation of that? Let's see. Another class. And I'm forgetting this part. Not that it's really needed, but okay, so implementation of this one should also be really simple. We are still getting in the constructor a dictionary because to simplify the benchmark code that will call this part, we'll always pass the same thing in, and then try get basically. So in here we create a tuple in the array. We transform the dictionary into an array of a tuple with a route and the endpoint. So what was the key and the value in this case are just two parts of the object that is inserted in the array. So try get just does a for each, and if path that starts with segments, this is a method from the path string, starts with path segments of route, then that's the endpoint we are looking for and we can return. So at first glance, what do we lose, what do we gain? What do we lose is, because it's not a dictionary, to index directly for a key, we have to do a for each, which depending on the size can or cannot be, may or may not be a problem. What we gain is that with using this starts with segments, there is no memory allocation, so this implementation will not create new strings, we'll just use the one that we pass to it. So now that we have the two implementations, it's time to test them, benchmark them, and see the differences. So BenchmarkDotNet is a library, and we install it in a console application, for instance, and create our benchmarking code. So let's start by installing BenchmarkDotNet. Installed. Okay, so what we need to do is create a class with some methods that should be benchmarked. So we pass them this class to BenchmarkDotNet. So let's start with creating the class here. I'm just putting it in the program. And to run BenchmarkDotNet, we can just do this. So to this benchmark runner class, we call the run method, passing the type that has the benchmark code. And in here, we'll need to call, or better yet, to use those classes that we created. So let's start. I'll start putting some things in here. That we need. So to test, we'll use some max routes. So we'll have some tests for like 10 routes, then 100 routes and 1000 routes to compare, because the dictionary implementation shouldn't be much affected by the increase in routes, but the array iteration version probably will be affected. We'll grab a string, a path string, which is will simulate the request path, and then we have the two implementations we created. Now I'll create here a method that is marked with this attribute global setup. So this means that BenchmarkDotNet will run this setup method just once before running the benchmarks. If you already created unit tests, you'll see that this is similar to unit tests, where you might want to do some setup before all unit tests, or maybe before just one unit test. In this case, it's for the benchmarks, which is kind of similar. We can think of these benchmarks as something like unit tests, but for performance. Okay, so in here, need another helper method. I'll put it down here. A create route, which will basically just create a dictionary, which will map a route to a route endpoint, just for tests. and he'll get max routes. So by doing this, in the setup we can call it with max routes. I put it in the wrong place. So we can create a route map with the max routes. So in the tests, we'll be able to use various max routes. We'll see how in a bit. Then we'll need to set that path to something interesting. So we are simulating that we got a request for a route, max route. And why I'm doing this, it's if I put just 0 or 1, the array iteration would always be very fast. But by using the max route, it should take a while to get to the max route. So basically I'm simulating the worst case scenario. Maybe it's not the best test ever to always do this, but should be good enough. And then some more things in the path just to make it bigger. And then we can create those classes, those instances to run. And now we can just create methods to call. So we create a couple of methods. These are the methods that will be called by BenchmarkDotNet to really run the benchmark. And to do this, we mark them with benchmark. I add this parameter baseline. So this it means that this benchmark method is the one that's the baseline, like the name implies. So we're comparing the others to this one and trying to figure out if the others are faster or not. That's why the baseline is here. And that should be almost it. Now we can just do something. So you might be wondering how these max routes will work. I didn't put any value. So again, like in some unit test frameworks, that we can use attributes to put values that change. In here we can put also an attribute, in this case params, with 10, 100 and 1000. So this will be ran for all three types. So each of these two methods will be ran once per each of these. Additionally, if we ran this just like this, we get some results, but we can add attributes or you change configurations. For instance, I will use attributes, but if I didn't want to, we can pass configurations here, the run method. We can pass a config. So we could do something like default config and add configurations. And there are a lot, but like I mentioned, I will stick with the defaults. For instance, I'm not going to go with that, but for instance, the BenchmarkDotNet does a number of iterations. It doesn't call the code just once, it calls multiple times, so it can do like averages, medians, errors, standard deviations, and stuff like that. So, but we'll use the defaults, but we could also change those values. But besides that, we can use attributes to change the output or even change the way it's done. So I'm going to add these two. There are more we could use. The rank column is just to appear there a number saying which is number 1, number 2, number 3. Memory diagnoser will show us the memory allocated by the code we are running, not just the speed. If we didn't put this here, it would just show us in terms of time, but we also want to see in terms of memory consumption. So we have it ready, so let's benchmark. We go to the console, and no need to go to the console, but I liked it. BenchmarkDotNet run. And then one thing that's important is pass the configuration as release for the benchmark to run with optimized code. Otherwise we would run in debug and the code wouldn't be as optimized. And it ran. And if I didn't do anything wrong, it should start. Okay, so it starts and we see a lot of info that I don't understand all, but you can see things like warm up. So it now takes a while. Shouldn't be too much right now, but because we have just a couple of benchmarks, but will take a while nonetheless. And the more benchmarks we add, the more time it takes. So just for us not to be stuck here watching this, I will pause the video and get back when the benchmark is done. Okay, so the benchmark is done and we have here the results, which could be nicer if it weren't that big. But you can see, start of a summary, it says the version of BenchmarkDotNet, the operating system, some hardware information, version of .NET, the just-in-time compiler, and stuff like that. Then we have a table with the results. So, like I mentioned, max routes was used with 10, 100, and 1000. And then we have the methods and the differences between them. So, the version that uses the dictionary, even with just 10 routes, is a lot faster. So 41 nanoseconds versus 170. Then we have more things, error, standard deviation, ratio. So the array version is 4 times slower than takes 4 times the time than the dictionary version. Rank 1 and 2. And this is the memory part. This is what is added by that attribute that I added for my memory diagnoser. So we can see that the second version, even though it's slower, doesn't allocate any memory. So nothing is put on the garbage collector generation 0, 1 or 2. But the other versions, some things are put in gen 0 and 136 bytes. Not a lot, but some memory. And then we can also look at the other versions. In terms of allocations, it's the same, but in terms of time, the dictionary keeps the timing, but the array goes south as expected. With more routes, becomes a lot slower. So, given this example, these results, I think the way to go is with the dictionary. But even so, it would be great if we could do the same, but without these allocations. So maybe we can play a bit with it and try to figure it out. Just before that, just for information regarding actually BenchmarkDotNet, besides this information that we get on the console, if we go to the code, a new folder was created with BenchmarkDotNet artifacts, which has logs of what was written to the console. But besides that, we have results, which is like a summary. We have in Markdown form, which is nice for just to copy paste and put in GitHub, for instance. And there's also CSV and HTML. The only one that I have used were the Markdown, but it's nice, those options. Okay, so let's get back here and try to think of ways if we can improve this or not. You probably already have some ideas how I'm going to try to improve this, because I talked about it here. So we'll try to iterate on the original idea of the dictionary idea with other things, starting with a span. So a span is a new type created in .NET Core 2.1, if I'm not mistaken. That, and let's go to the docs, provides type and memory safe representation of a continuous region of memory. What does this mean? That it provides a way to have a window to memory, type safe, so no need to go all C++ on the code and directly go into memory. No, we can use the span for that. And provides a window to memory. So what does this mean? Let's imagine in the case of string, this does more than just strings, but imagine the case of the string. We can, for instance, have a string of 5 characters, and we say, I don't care about the first one, don't care about the last one, so I just want to see the 3 in the middle. So we can see them like a window, like if we did a substring, but not actually a substring, so it didn't create a new string. It's just showing us those 3 characters, but in reality they are in the middle of a complete 5 character string. Just is showing us a span as if it didn't. So it's just showing that region of memory. So looking at the code, let's create a new class. Ignore the name for now. My proxy stuff. Okay, so I'd say the first idea that would come to mind is we want to use this dictionary but instead of a string, in reality we wanted a span of char. The problem is, as you already can see, we can't, because span, for some reasons that I'm not the best one to explain, but the span can only live on the stack, cannot live on the heap. So if we put it in the dictionary, it would end up on the heap, and it can't. If we look at the specification for span when it was created, it seems the reason is because of struct tearing. So in some cases, apparently on 64-bit processors, it wouldn't be able to be updated atomically, so it would need synchronization, and because synchronization would make it slower, and the focus of span is to help improve performance, instead of synchronizing the access and stuff like that, they simply said, okay, we can only use it from the stack, we can't put it on the heap. So it's a decision they make, so we can't do this. So this is going away. The next idea that came to my mind was, given they are so focused on using span to improve things, and for example, one thing they are doing a lot with span is with ASP.NET Core. They use a lot of span because ASP.NET Core is very focused on string, because being a HTTP application framework, HTTP is a lot string based, HTTP request, response, and all of that. So they want to improve that performance. That's why span is really important. So I thought maybe they have something like a way to index a dictionary, even though it isn't a span, but given a string, maybe there's a way. So I wasn't the first to have this idea, as expected, and there is an issue, but it's open. So it seems maybe in the future it will happen, but right now it's not possible. But in the future maybe it will occur, so we will be able to try to get index the dictionary using a span, or read-only span, as you can see, because actually a span in case of a string is a read-only span because the string is immutable. So maybe in the future this happens. Right now, not done yet. So what can we think more? We can't use it directly, in the dictionary. We can't index directly in the dictionary. Maybe there's some other idea. So what came to my mind was the implementation of the dictionary is based on get hash code. So if there is a way for us to use the span to get the hash code just of the window it's representing, we could, instead of indexing by given the string or the span, we could index directly with the hash code. That wouldn't be enough because the hash code might have hash collisions, so we need to have a list of all the possibilities, but still it's a possibility. So that's exactly what we are going to try. So let's start. I'll create a couple of dictionaries. I'll use 2 dictionaries, and you'll see in a bit that I shouldn't, but let's start with really the simplest thing that came to my mind. So 2 dictionaries. The first, the order is wrong, but okay. So this first one is an integer, so this is directly the get hash code. We will get the hash code from the span and index in the dictionary to try to map it to the actual string part of the base path of a route. Like I said, as the get hash code might have collisions, we'll have an array of strings. So after we index, we'll go through the array and try to find the exact match. So we'll make use of the get hash code and equals to be sure that we index to the correct stuff and avoid routing requests to the wrong place. After that, after we find the exact string, we can then index on the second dictionary, that is string, and this one is the one that will return the actual route of the target API. So I'll grab a constructor that I already prepared. So this one is simple. We just put it directly. The other one, we need some logic. So wait, what am I doing wrong? Okay, this is string directly. This one, okay. So this one, the key will be the get hash code and all the values, and we're grouping by, so just in case there is a collision. From the test I made, there were no collisions, but you never know, depends on what are the keys we are using, so better safe than sorry. So we're grouping and then creating a dictionary out of the group with the key and the array. And now the implementation. The beginning of the implementation might be familiar. So let's see. This is basically what we had before, but instead of using string stuff, we first do as span and then we slice. So we remove the first character because the first character is the slash, and then we remove the first one, and then we grab the index of the second one because we just want the first segment. That's why we are doing these shenanigans. And here we can do the slice again, ignore the first one and go until the end. So we just grab the first one. But in this case, instead of a string, this is a read-only span. So we are not creating new strings. The logic is exactly the same as the first approach, but we are not allocating strings. Now comes the weird part. Using this base path, we try to get a value of all the routes. And if we get all the routes, normally it will be an array of 1, but we need to be sure. Then we find it in there. I'll create here an helper method, find route. So it will for each on the route and compare to that one. And I was forgetting, the key part is there's a static method on string named getHashCode that is able to get the hash code of just the segment that the span represents instead of all the string completely. If we called getHashCode on the span, it wouldn't work because it would be a different hash code. The string.getHashCode will get you the hash code as if we are calling that on a substring, on a real substring, and not just a window substring. And now we can just put here return false, because if it doesn't enter this if, it's a failure, it didn't map the route. And in here, what we'll do is find the route given the base path and the route, and if a route is not null and we are able to map to the second dictionary, then it'll work. Okay, so this one, from all of this, what we expect, given we are using two dictionaries, we are avoiding allocations, so what we are expecting is not having any allocations, but taking the double the time, because we are indexing twice instead of just one, so double the time, maybe a little bit more. But how are we sure? We benchmark it. So we'll go here and add the new things. Add this new class, prepare it, go down here, add it, okay, and we'll run the benchmark again. And I'll do the same as before, so I'll start the benchmark and I'll pause the video recording and we'll get back here at the end of the benchmark. See you in a minute. Okay, so we're back after running the benchmark. Let's see the results. So what do we have? Basically, as expected. The other two we already saw, sorry. And this one, with this giant name, is more or less what we expected. It's about double the time of the first one, but doesn't allocate anything. It's faster than the other one, and as the first one doesn't really have much impact with more routes, so that's what we expected. So maybe it's a nice compromise between the first one and the second one. Honestly, in terms of the speed and the memory usage, I'm not sure what is the best, if we should just go with the fastest one and ignore these bytes that are used, or if it's best to be a little slower and don't allocate anything. I'd say maybe we need more metrics in production to make more decisions about this, maybe taking into consideration what the garbage collector would cause in terms of this. I'm not that focused on performance stuff to be sure on this regard, but just wanted to play around a bit with BenchmarkDotNet. But yeah, maybe this one is a nice solution. And maybe we can play a little bit with some more concepts. But just before thinking about this, a couple of hours after thinking about this solution, I thought, I'm an idiot. Because why do we need to have two dictionaries? We could do basically the same. The core idea I don't think is completely wrong, but instead of having a string array, we could have an array of a type instead and remove this part altogether. So let's do that version. We'll create a new class. Yes, I proxied things. And I'll just copy everything because it's mostly the same. So let's see. Forgot the So the constructor is basically the same or similar than before, but in this case, let's start. We need a dictionary with an int which is the hash code, and instead of string, we just have a holder. What is this holder? It just has the route and the endpoint. So basically, instead of having two dictionaries and indexing the first and then the second, we put the values of both directly in the first one. Instead of two indexes, just one. So it's kind of obvious, but didn't came to mind immediately. So here we're preparing that. We get the dictionary in the constructor and then go through everything. And if there is already there, I'll add a new holder to the existing array, or better yet, the existing list. Otherwise, I'll add to create a new list. In the end, I just transform the list into an array for no good reason, just because I want an array in there. And now let's get to try get. So try get is the same, but instead of indexing again in the end, we can get the value immediately. So when we find the route, we return the endpoint. If the endpoint is not null, we set the endpoint on the out parameter and return if the endpoint is different from null. So this should be still slower than the first approach, but should be a bit faster than this third one, just because it's exactly the same without two dictionaries. So let's again go to the program and add the new thing. Program, new thing, create a new instance of it, and call it. Okay, so now benchmark again. You know the drill. I'll be back in a minute. So back with some results. Let's see. Nope. Let's see what happened. So looking at the attempt 4, it's better. The rank, this is all messed up. Maybe it's better to look at the markdown. Or not really. Let's see. Okay, it's better. So the attempt 4 is still slower than the first one, but it's a bit better than the third one. So we got rid of those double indexes and just have the other shenanigans. And in terms of rank, it's number 2. So it's better. It's a better solution. So just before wrapping up, we can just take another look at some other interesting things, not because I think it will make a lot of impact, but just because it's interesting to discuss the possibilities. Looking here at this approach, honestly I can't remember any other improvement right now. Besides one that will probably not be a lot of improvement, but it won't harm to try, which is this find route method. This is something we normally ignore because I think we should, when we are doing business related code, we should have our classes and methods well separated, so our code is decoupled and it's easier to read, so we call all those methods to see how everything goes, and that's why I created this find route here instead of putting this code in there. But in performance sensitive code, a call to a method has some impact. It might not be a lot and depends on the method at hand, but might have. So the compiler sometimes does something which is called inlining. So basically, even though we have the code right here like this, it will create it will grab this code, not the compiler, not the C# compiler, but the just-in-time compiler. So C# will compile this to intermediate language, and then when .NET is running this code, we'll convert that intermediate language to actual machine code. And in that process, sometimes if the just-in-time compiler thinks it's worth it, it might try to grab this code and put it directly in the other method. So we don't know if the compiler is doing that or not. Maybe it is, maybe it isn't. If it isn't, maybe it would be nice if it inlined the code. There are conditions to do this. Not all methods are inline. So the compiler has some metrics when it should or should not inline a method. So check here, this blog post by Matt Warren has some of the ideas. So let me check. So inlining rules, these are from an older article, but maybe they're still applied. So we can say the method shouldn't be inline, so it would avoid the IL could be too long, virtual calls, value types, blah blah blah. So a lot of rules when the method is inline or not. Feel free to investigate more. I would just want to discuss a bit the concept. So how do we know if this method is inlined and if we get anything out of it if it is? So as usual, BenchmarkDotNet does exactly that, help us with that. So we can try there's a NuGet package, which is BenchmarkDotNet diagnostics windows. Can install it, and then we can add a diagnoser to know which methods are inlined. And I'm log failure only false, so we can see all the methods that are inline or not. So let's try to run against the benchmark and find out if this find route method is inlined. You know the drill. I'll be back. See you in a bit. Okay, so the benchmark ran. Just before seeing the results, I forgot to say something. Looking at the NuGet package, the diagnostics windows, this is because, from what I understand, this part with the inlining diagnoser and stuff requires ETW events that are only available in Windows. Maybe in the future some events are available in other platforms, but I think for now that's why I needed to install this Windows only part, because that requires ETW events. So let's see. So the result should be the same, but in this case we have this part which talks about what was inlined or not. The blue inlined, the red no. So looking here will be a bit annoying, so let's go to the code. You see the results, I think it's the last one. Okay, inline. So let's find route. And what we are looking for is to find route as an inlinee. So let's see. Find route, inliner. Okay, over here, find route wasn't inlined. This was for attempt 3. Now this is for only attempt 3, so attempt 4 never talks about inline, which is what we wanted. So even though inline 3, in attempt 3 says it should inline, let's try it anyway. So we'll create basically a copy of this 4th attempt. Let's create a new class. I proxy things, which is basically the same. But the find route has this attribute, method impl options aggressive inlining, which means we are telling the compiler, the just-in-time compiler, please try to inline this. If you find out that you can, please do it. So if the compiler thinks it's not useful, it won't anyway, but let's try. So let's go again to the program and add the new benchmark. So the code is exactly the same as the 4th one, with a difference of the inlining. So let's benchmark and try to find out if it does something useful or not. We could also inline manually, but we would lose the readability. So let's try again. And be right back. So benchmark done, time to look at some results. Before looking at if improvement happened, let's start by seeing if inlined happened. Try get attempt 5 inline, so this time find route was inlined. So in terms of results, let's go to the results. Okay, so comparing with the 4th attempt, it improved a couple of nanoseconds, so not a lot, probably negligible, but okay. We at least had the opportunity to play around with something different. And that's the theme for this episode. As we finish up, the main gist of the episode was BenchmarkDotNet is a nice tool to play around with benchmarks, of course, help us a lot. If you noticed, our program class where we configure the benchmark is not that hard. We just call the code benchmark, so call tryget. We created this part, just typical setup. We need the classes to call the code. Couple of attributes, benchmark, global setup, this params stuff, some more things to give us more information like the rank, the memory usage, and this more hardcore part, the inlining diagnoser. Running is simple, and these classes are the same as we would use. So basically what I'll do is copy this class and put it in the web application, so we use this version. And yeah, besides that, just right off the bat, I'm not really a great performance guy. It's not something I do regularly, but it's nice to have these notions. So when we are doing our code, we understand that, oh, maybe this could be better. Oh, maybe this could be better. But of course, when we are doing line of business work, we probably won't worry about a method inlining and stuff like that. Span is another question. If we see that we are manipulating a lot of strings, of course we don't optimize prematurely. We just write the first version and work with it. But maybe if we start seeing a lot of string stuff going on, maybe we can try to think if span can help us. But yeah, the goal of this episode was more for us to play with some things a little bit different, maybe not completely related to the application we are developing, but as this is .NET Core or ASP.NET Core from zero to overkill, this episode has some overkill parts that we don't method inline daily, but I think it's nice for us to know. And of course, this part, the execution type and the memory allocation are important things. Normally we just think, we want this faster, but we forget that if to make it faster we use a lot of memory, the garbage collector will have to work in the future, so not great. So hope you enjoyed the episode. As usual, always feedback is welcome. Feel free to open issues or PRs with ideas to improve the code. I'm pretty sure this is not the best we can do. We can do better, but it's good enough, and we got to play with interesting things. And ask some questions if you had. But again, I'm not a great expert on spans, inlining, and all of that. But at least I hope I piqued your interest in some of these subjects that, even though are not day-to-day for many people, are things that are interesting to have some ideas about. So again, hope you enjoyed it, and hope to see you in the next one. See yas!